Hey everyone, and welcome. Have you ever used something like ChatGPT and just been blown away by how it seems to, well, get you? It understands the little nuances and the context of what you're asking. Well, the secret sauce behind that isn't magic. It's a really brilliant idea called the attention mechanism. This was the breakthrough that let AI really start to grasp long, complex thoughts. And today, we're going to pull back the curtain and see exactly how it works. Let's dive in.
So it really all starts with this one fundamental question. If you give an AI a simple sentence like, "The cat sat on the mat," how on earth does it figure out that the word sat is most connected to cat and mat and not so much to the? How does it know where to focus?
The answer is something called an attention function. The best way to think about it is like a spotlight. Imagine a long, complicated sentence is a dark stage. The attention mechanism lets the AI shine a bright spotlight on just the most important words for that specific moment, giving them more weight, more attention.
So here's our game plan for today. We'll start with what AI attention really is. Then we'll look at the three key ingredients, the vectors. We'll walk through the recipe for how attention is calculated. After that, we'll see how it gets supercharged with something called multi-head attention. And finally, we'll see where it all fits inside the famous transformer architecture. Okay, so at its core, AI attention is basically a sophisticated system for finding the right information. Before this, older models kind of had a short-term memory issue. You'd give them a long sentence, and by the end, they'd forget what happened at the beginning. Attention was the breakthrough that let them look across the entire text, no matter how long, and map a specific question, what we call a query, to the most relevant bits of info to give a single, context-rich answer.
So how does this mapping actually happen? Well, it all comes down to three absolutely essential components. In the world of machine learning, we call these vectors. Don't let that term scare you. You can just think of them as simple lists of numbers that capture a word's meaning. And these three vectors are the only ingredients we need for our entire attention recipe.
Let's use an analogy to make this crystal clear. Imagine you're in a giant library. The question you want an answer to, that's your query. Now, you're not going to read every single book, right? Of course not. You'll go to the card catalog and look for relevant titles or topics. Those are the keys. And once a key matches your query, you pull out the actual book, which has all the rich information inside. That book, that's the value. The attention mechanism is just a way to do this whole process automatically with words and data.
All right, we've got our ingredients, the query, the key, and the value. Now let's check out the exact recipe that transformers use to cook this all up. It's called scaled dot product attention, and honestly, it's a surprisingly elegant process.
Okay, this diagram here is the official one from the original Attention is All You Need paper. And yeah, I know, it might look a little intimidating at first glance, but the core idea is really just a simple 5-step recipe. We've broken that recipe down for you, so let's walk through it together right now.
So here's the recipe. Step 1. Dot product. This is just a fancy math term for measuring similarity. The model takes our query vector, our question, and compares it to every single key vector in the sentence. A high score means they're a good match. Step 2. Scale. This is basically just a bit of housekeeping. We divide all those scores by a number to keep our math stable. Simple. Step 3. Mask. Now this is an optional but really clever trick. Sometimes you want to stop the model from cheating by looking ahead at words it shouldn't be able to see yet. That's what masking does. Step 4. Softmax. This is where the magic happens. Softmax is a function that takes all those messy similarity scores and neatly squishes them into clean percentages that all add up to 100%. These percentages are our attention weights. And finally, step 5. Weighted sum. We take those attention weights and multiply them by the value vectors. So words with higher attention get a bigger say in the final output, creating a new vector that is just packed with relevant context.
So this is the absolute key takeaway. That softmax step, step 4, it creates this set of percentages or weights, and those numbers literally tell the model how much importance, how much relevance each word has to the word it's currently looking at. It's a numerical way of showing focus. And believe it or not, that entire 5-step recipe we just went through can be summarized in this one single formula. Don't get bogged down in the math, just look at how the pieces fit. See the QK-tran? That's our dot product from step 1. The little square root thing? That's our scaling factor from step 2. The whole thing is wrapped in the softmax function, just like in step 4, to get our weights. And then it's all multiplied by V, which is our final weighted sum from step 5. The whole recipe, right there in one line.
So that's scaled dot product attention. Awesome. Problem solved, right? Well, not quite. As powerful as it is, a single attention mechanism has one big limitation.
Sometimes just one point of view, just one look at a sentence, isn't enough to capture all the complex relationships going on.
Here's the issue. A single attention calculation is kind of forced to learn an average of all the different ways words can be related. But think about it. Words have all sorts of connections. There's grammar, there's meaning, there's just their position in the sentence. Forcing one mechanism to learn all of that at once is a huge bottleneck.
And this diagram shows the absolutely brilliant solution: multi-head attention. Just look at this. The Q, K, and V vectors come in at the bottom. But instead of going into one big attention process, they get split up and fed into several smaller attention processes in parallel. Each one of these is called an attention head. They each do their own analysis, and then their results are all stitched back together at the end. It's like having a whole team of specialists looking at the same problem at the same time. So let's put this side by side, because this is where it really clicks. A single head gets you just one perspective, but multi-head attention gives you multiple perspectives, all at once. It's the difference between having one person analyze a complex problem versus having a whole committee of experts where each one focuses on a different angle. The final understanding is just so much richer and more robust. This multi-headed approach just completely enhances the model's power. Different heads can actually learn to specialize. You might have one head that gets really good at tracking grammar, while another one tracks who did what to whom. By capturing all these different patterns at once, the model gets the amazing performance that we see in today's best AI.
Okay, so now we have this incredibly powerful tool, multi-head attention. For the final piece of our puzzle, let's look at how the transformer architecture, the foundation for models like GPT, actually uses this tool. It turns out it gives attention three very specific and distinct jobs to do.
So there are three main jobs. First is encoder self-attention. This lets every single word in the original input sentence look at every other word in that same sentence. This is how it builds up a deep understanding of the source text. Second, there's decoder self-attention. This is similar, but it's for the sentence the AI is generating. It lets each new word look back at the words it's already written. And third, you have encoder-decoder attention. This is the crucial bridge between the two. It lets the part of the model that's writing the output look back at the original input sentence to make sure it stays on track. This is absolutely critical for things like translation.
And really, it all comes down to this. The entire point of the attention mechanism, in all its forms, is to let the transformer build a deeply contextualized understanding of every single word. A word stops being just an isolated dictionary definition. It becomes a word that is understood in rich relationship to all the other relevant words around it.
And that leaves us with a pretty fascinating thought to end on. For decades, one of the biggest challenges in AI was just getting machines to focus. Now that they can genuinely pay attention with a level of nuance that feels almost human, it blows the doors wide open. It makes you wonder, what complex ideas, what subtle human contexts, what new frontiers will they understand next?